Welcome back. In this video, we will discuss again about textual analysis, but with two well-known Python libraries for NLP. They are called NLTK and SpaCy, and they are each offering a range of features to work with and analyze text with. The first one, NLTK, this is one of the earliest libraries in NLP, and it includes tools for stuff like tokenization, stemming, lemmatization, parts of speech tagging, and named entity recognition, for instance. And it's widely adopted both in an academic setting, but also in industrial NLP applications. And the second one is SpaCy. This is a more recent addition to the field of NLP, but why people prefer it is because it's quite fast and efficient. And it provides also pre-trained models and pipelines for tasks like tokenization, parts of speech tagging, dependency parsing, NER, and sentence boundary detection. SpaCy is also used a lot for production level NLP projects, exactly because it's very performant and it's not so difficult to use, as we will see soon. So what we're doing here, first of all, we are installing NLTK. I have done this already, so I'm not going to do it again. We are importing it. And then we are downloading this package of stop words from the NLTK corpus. And the first thing I would like to try, some more complex EDA, is to look for the non-stop words in our corpus and create a bar chart. So what we're trying to do is we are plotting the frequencies of these words that are not stop words. We have to remember that these non-stop words are quite important because they are conveying the meaning of the sentence. So what we would like to do in general is to remove them and then focus on the rest in different machine learning models. So, but if we look now at this snippet of code, what we do first is we import Seaborn for data visualization, like you've seen many times before already. And then we import from collections this counter class, which essentially helps us count the word frequencies after we separate the stop words. And if we go into this very function of plotting the non-stop words, first of all, we create a set of English stop words. So here in this line, and that what we're trying to do is to split the input data. So it takes some text form as an input and convert that split text into a list of words and then flatten that list to create a corpus. So here we have the corpus. And after we have the corpus, we count the occurrences and we get the list with the most common occurrences, right? So this is what we're trying to do all along. So if the word is not a stop word, you remember we created a set of stop words there, then we create this list with a set of words, and then we append in wide and frequencies for the bar chart. And after that, we plot essentially this y against x right over here. And I took, if you remember from the previous video, we had this title df in which we took for convenience the title column of this A data frame. So if I plot this, then we can look at the most common non-stop words in this title column. So the first one, remember that we are using this space news CSV dataset. So of course, the most common is not a surprise that is space. Then the second one, NASA. The third one is low case space. So this we can really change to combine them maybe in the same entry if we want to. Then of course, satellite, SpaceX, air, launch, and so on. Now, just out of curiosity, we can create the same kind of a bar chart for stop words. So what we're going to do is we're going to split again every entry, and then we're going to create a list. We're going to create our corpus. Then in that corpus, we're going to count the frequencies of stop words for this time around. The code is very similar to the other one, so I'm not going to go over it again. Then if we plot it, so the most common stop word is 2, then the second most common is 4, the third most common is off, and so on. And what we would like to do, like I said earlier, in many applications, that is that we remove the stop words because we would like to input the corpus without the stop words for machine learning algorithms to train different models. So let's look into that now. So for the stop word removal, first of all, we create a set of stop words again. We could have used the one before, but I wanted to remind you that you could also add custom stop words if you use this use option. And then we create a function to remove the stop words. So what we do is that we, again, split the text, and then we iterate through each word in the list that we obtained from splitting and check in this line and then check if the word after stripping the white space is not in the stop word set. And if the word is not a stop word, if it's not in that set, then we will add it to a new list, essentially. And then we get in the end, what we return here is the modified text with the stop words removed. So if we applied this to our title df data frame, which if you remember, it was the first column of titles from our dataset. I would like to make a copy of it because I always like to play it safe. So let's see. So we did that. And now let's do the following thing. Let's check if anything happened. So we are gonna, maybe I'm not going to need that at all, or actually maybe I do. But what I'm actually not gonna do it. So what I would like to see is the title. So we are taking this entry on position 2057, right? And check in the original data frame and in this new data frame. So this is with the stop words and this is supposed to be without stop words. So let's see if the function worked. So this is China launches 14 satellites with new solid rocket from Mobile C platform. And then the second one is China launches 14 satellites. And then with, this is one stop word is removed. This is another stop word is removed. A lot of the time you can add these stop words, and this is why I was mentioning this option. For instance, if you don't really care about quantitative data, if you are doing some kind of qualitative analysis later on, then you could also add numbers in the stop words, or depending on what kind of analysis you do, you can add different kind of things. And then we're gonna start looking at SpaCy. So here we are installing SpaCy, and we are also downloading this English language model. This is the small version, by the way. There are many different versions. You can check online already. And what we will do next is that we will load that specific model. So first of all, of course, we import SpaCy. This is to display later on. For instance, if we do lemmatization or dependency parsing or other things, you can use this displacy to just check the parsing. And then we log the English model and pass the object to be used later. To be used later. Gonna correct that. I corrected it. So, okay, that has been working out. And then what we would like to do is to do lemmatization, right? Why not? One thing I forgot to mention, so we have this lemmatization function, but just before we are loading the model, and what we're doing is that we're turning off the parse and then the named entity recognition modules or components, let's say. I think the actual term is components because we don't really need them for lemmatization, and then it can speed up the computation. So for the lemmatization functions, we are inputting a string that is going to be lemmatized. And then we can input also a list of allowed parts of speech tags. So like noun, adjective, verb, adverb, and so on. And the way this works is that we are iterating through each sentence, like from the input. And then we process that sentence with our NLP model, creating this doc object that we have seen before as well. And this contains all the linguistic information in the sentence. So what we're doing here is that we are accessing the lemma of the current token to include only the tokens that consist of alphanumeric, sorry, not alphanumeric, but alphabetic characters. So actually no numbers on or punctuation. And we include only these tokens that are in the allowed post tags that we defined over here. And then we exclude the stop words from the lemmas. And after we did that, we are returning the lemmatized output, essentially. And if we give this a try, let's see how the tokenized titles look like over here. Well, actually, I have not done anything with them. So the next thing we're going to do is to visualize this tokenized title, just like we visualized stop words before. So to visualize them, we make a list with all the tokens and we get the top and most frequent ones. So I chose the most frequent 20. We extract their accounts and then we create a bar chart like we did before. So, and then we can see the top 20 most frequent tokens in tokenized titles. We can see that they're a little bit different than what we got before. And this is because we're using a completely different language model, a completely different package, and so on. So depending, we also did lemmatization. So depending on what you are doing, you have to be very careful what library you're using and exactly what that library is doing, because you might miss things. And then with really big data sets like this, you can get completely, well, not completely, like slightly different results, but you can really influence something in the pipeline, and then it might become, uh, well, you can make erroneous decision essentially because of it. Then if we want to plot the n-grams, this might be a little bit of a more difficult part of the code, but what we want to do is to extract and count the frequency of n-grams from a text corpus. So what we do in the beginning, in this first part is quite simple. In the end, we have done this already like 3 or 4 times by now. So we input the text data, we split it into individual words using space delimiters. Then we convert it into a list, and then we create a corpus. So this part we have done many times. We set the stop words and so on. So the second part, what we're trying to do here is to um, transfer the corpus into a bag of words, essentially. So here we are trying to create a matrix where the rows represent a text and the column represent an n-gram, essentially. And then to calculate the sum of each column across all the rows, right? And then at the end, create a dictionary that maps these n-grams to their column indices in the matrix. So this is what this part of the code does. You can play with it, you can debug it if you have the time, and then iterate through that dictionary and retrieve the corresponding count. And then at the end, what you would like to do is to sort the list you got into a descending order based on frequency and then the top n-grams. So if I run this and then we plot the n-grams, so I chose the bigrams here. We can see that the bigrams are the most common are Air Force, Space Force, OPED, Space Station, in space, to launch for space and so on. Remember, this is obviously not lemmatized and so on. So we also have the some of the stop words here. But now if I change that to 3, we are gonna get trigrams. We have space development, Agiteo, national security, OPED, and so on. And now, since we did this, it's time to use maybe this SpaCy for a second to just show you what it does. Okay, so maybe first of all, I would actually take the opportunity to show you what's in here. So what I wanted to take is this sentence, essentially. It's one of the titles of one of the articles. So SpaceX sets early June launch of next Starship test flight. And then if we create the NLP model of this is what we can find out with SpaCy. With this SpaCy, which is essentially part of SpaCy. So what this SpaCy does is to visualize. It's a dependency tree visualizer. So it creates this tree based on the text you have given it, and words are connected by labeled args, as you can see, and they define their syntactic relationships. So how you do this is that you create this kind of um, model here like we had before, and then you render this tree by specifying this style, which means dependency tree, essentially, and then you get the dependency tree. Now we can check for other things in this SpaCy. So another thing that you can do here is also named entity recognition. So if we take the same example, this is quite easy to do. So we have the same line, and then what we want to display is named entity recognition. So we choose this. And then we have this SpaceX, set early June date and launch of next Starship. Well, this is not entirely correct. So all of this can be changed. And obviously SpaceX can be recognized as a company and so on. But just to give you an idea, you can refine this by yourself if you want, but this is one way to do it. And what's important to remember is this model here has different pipelines. So it has a tagger, a parser, a lemmatizer, named entity recognition, and so on. You can get the same thing if you try to print this line. And then if you want to just get the component names, over here you get them like this. And you might been wondering why I have looked at these component names and so on. This is because the next thing we will do is sentiment analysis. To perform this, then we are going to use this package SpaCy text blob. So we can install this and download its corpora. I have already done it, so I'm not going to do it again. And oh, and I did it twice. This is then we import it. We already have the model. So what we want to do is to add this in the pipeline that we didn't do before. So this is the reason why I wanted to see what we have in the pipeline so that we could add that there. And then I took a text from one of the articles. I created a new doc with it actually, and then I checked for the polarity, for the subjectivity, and for the assessments. So we run this. And then let's see what is happening. So we get a sentiment score for 3 words, right, wrong, and big. And what we can read is that the right has a positive sentiment, and then wrong has a negative sentiment, and then big has a neutral sentiment. And then you can play with this and do a lot of more things. But I'm going to stop here, and thanks for listening. See you in the next video.